Yeah, thank you for your introduction. I will start the talk. So our talk is basically about cloud security with LibVMI. LibVMI, a library that was built mainly by Tamás and Brian. And the outline of this talk is like, first we want to a little bit define what we see as cloud security, what are the problems of cloud security, and followed by that, looking a little bit at the hardware security mechanisms that are supported by modern CPUs nowadays. Then we will have a little bit of a look at what is virtual machine introspection, why virtual machine introspection. Then we will introduce like what is LibVMI, what can be done with LibVMI, followed by a couple of demos and a conclusion, like what's next. So the first thing that we want to talk about is like what is the cloud. If you talk to different people, for example, from management, they see cloud as something that where they can like save money, and like the different people that look at the cloud for certain reasons have also a different understanding for what is cloud security. For example, an end user has the problem like if I put my data into the cloud, like is it secured? How is it privacy? Are the privacy aspects of the security? But like we say, if the data is like given to another provider, there's nothing we can do. So this is not what we are really pretty interested. Another thing that could be interesting for cloud security would be like legal aspects. May I give the data to another country or whatever? And that's also not the problem we are focusing. So the important thing that we think of as cloud security is like how can we leverage security mechanisms that are or mechanisms that are used for the cloud and use them to enhance security of cloud systems and also apply these security mechanisms then back to end user devices. So we are like the researcher's point of view thinking about the security mechanisms. Who is interested in or should be interested in cloud security? Mainly cloud providers should be interested in cloud security because they are like running the hardware, running the virtual machines, and for them it's like the money. Yeah? If the virtual machine, if the cloud goes down, they really use money. While also you don't have only like the infrastructure that runs your virtual machine, but you also have your applications, made web applications and databases, and those have to interplay with each other somehow. So the application programmer, the application developer should also be interested in those techniques that we then introduce to monitor their systems and see whether there's an anomaly going on or not. The end user in this view like has little to do with the cloud security as is, because for the cloud scenario, he, as here on the slide, he can only change his password. He has no access to the actual hardware. But as we will tell you, there is a possibility to use those mechanisms also on end user systems like the ones that you have so with you. So what are the problems of cloud security? What should we think of? Well, there's the fundamental problem of if you talk to people with what is cloud security, then you have the big problem that malware could execute on a virtual machine in the cloud and try to break out of the virtual machine, infect the host, and thus infect the entire cloud environment. While this is possible, and there have been such attacks, this is not the biggest problem. So also in the cloud scenario, the usual network-based attacks, usual malware, is also targeting virtual machines within a cloud environment. And this kind of attack is much more probable. So an attacker will still use that kind of attack to infect the virtual machines that are running in a cloud environment. And we need to hinder the malware within the cloud by using the architecture and the security mechanisms that are in the cloud in addition to a classic host-based scenario. So for Oh, yeah, exactly. Sorry. And why is this interesting for you? As I already said, the techniques that have been developed for using for the cloud, so virtualization as a basis, is not only available in server systems that are dedicated, made for the cloud, but it's also coming on other devices, for example, phones and tablets. So the new ARM CPUs have also virtualization extensions, and thereby the mechanisms that we develop for cloud systems can now also be used in your machines to protect your data and your operating systems. And yeah, as a foundation, we will now introduce like the basic security mechanisms that are there in modern CPUs.
Thanks, Tom. So just really quickly, I want to put into perspective of where cloud security and virtualization stand as we have for modern hardwares. So for this, I have this slideshow that should be 5 minutes. It's a non-comprehensive history of how hardware-based security evolved and where we are actually standing today. So now we are actually going to deep dive into the matrix. So you might know that before 82, what we had is really just physical memory that now we call the real mode. Of course, before 82, this is like the beginning of Intel, for example. This was just what you had. So you had an application that was running on your system that had access to your physical memory. And if you had multiple applications, those were running in the same environment and they would have no barrier in between. So if one application was misbehaving, there was nothing in the hardware to stop it. In 82, protected mode was introduced that actually brought with it 4 protection rings. So these are called rings, but of course these have nothing to do with the geometric rings, so I'm just going to use a box to represent them. And to confuse things a little bit more, privilege goes down. So the most privileged one is ring 0, and that's where your operating system lives. And there can only be one operating system, of course. So you only have one process running in ring 0. And then on the top you have, in ring 3, you have your application. We have also ring 1 and 2, but those are really unused. They were available, it's just, who cares? And as I said, privilege goes downwards. And again, we have more applications. And the way to think about it is that we have more boxes on the top. So those are actually living in what's called virtual memory. They don't necessarily see each other unless the operating system permits them to interact with each other. And they interact with the operating system, what's called system calls. In 2003, of course, we started looking at virtualization. And one of the virtualization mechanisms was Xen. And the best thing about Xen was that it was actually using the hardware to push the operating system down into ring 1. And that enabled the operating system to use the native instruction available in hardware instead of using something like emulation or binary translation. And that also enabled more than one operating system to run on the same hardware. So Xen would take the the space in ring 0. You have your operating systems in ring 1, and on top you have the applications inside each virtual machine. Unfortunately, in 2003, 64-bit mode was introduced by AMD, which actually disabled ring 1 and 2. So it wasn't that it wasn't used anymore, it was actually disabled by the hardware. So of course, that kind of presents a problem for Xen. So what they decided to do, they just pushed the operating system down to ring 3 as well, and then just use a software-based separation of the operating system within the virtual machine and the application. This is, of course, very slow and not as secure as the hardware-based mechanism, but hardware-based virtualization was introduced in 2006. So this is the VTX extension on Intel and the AMD-V on AMD, where you actually have a ring -1 specific for the hypervisor. Then, depending on what operating system you're using within the virtual machine, ring 1 and 2 might be disabled if you are running 64-bit operating system, or it's just unused if you're running 32-bit. Of course, ring -1 is not really a ring -1. What that is actually is a completely parallel mode containing another 4 rings. So things are going to get a little bit more complicated, so I start color coding here. So now on the left we have, with red, you have the hypervisor, and on the right you have the virtual machine in blue, and the privilege goes to the left. So VMX root is more privileged than the right with the virtual machine. And of course you have multiple virtual machines running multiple processes, so now you start to pile boxes on top of each other. Of course, there is a secret mode in your CPU. That's the system management mode that has been there since '93, actually. This was really introduced for the BIOS and for the hardware manufacturers to hide errors within the hardware and for emulating, for example, USB devices and things like that. And that's what's called the ring -2. Of course, it's not just a ring -2, it's a completely parallel ring as well. So now we have 4 more rings on the left. I'm going to color that with green. Of course, that's not enough. Why not? We can just keep piling layers. So there is actually this secret mode within the secret mode that actually enables a hypervisor to run within the system management mode, and that's what's called a secure transfer monitor. And then on the right, you actually have virtual machines running within system management mode, and I'm going to be using the dark green to signify that's actually virtual machines within system management mode running on a hypervisor that runs another hypervisor that runs virtual machines that run processes. Let's add some more. We actually have ring -3. Has anyone heard of the Intel management engine? So what that is actually it's a coprocessor. So this is not actually a ring -3 either. Might not be surprising. It's actually a coprocessor. So this Intel management engine is turned on even if your main CPU is down. We don't really know what is running on it, except that it's some sort of Java stuff, which is kind of unsettling. And it's running on an ARC 600 processor, which only has a user and kernel mode, but has 16 of those. And that's the most privileged part of the system. In 2013, nested virtualization was introduced. So that is actually running a nested hypervisor on your main hypervisor, but in VMX non-root mode. So that's a dark blue. And what's coming next is actually the Intel SGX extension that's going to be released sometime within this decade, probably this year, next year, or whenever Intel decides that it's ready. And what that does is actually it carves out a space within ring 3 within your virtual machine, for example, so that you can load something into that mode, encrypt it, and then all of this stuff to the left that is running underneath your virtual machine doesn't actually have access to it. So they kind of realize that we have too many layers now, so you actually have to trust all that stuff that's running on that hardware before you can actually trust that your cloud is secure, so this is what they introduced. And of course, that's available in all of those modes. Luckily, this is not available in system management mode, so it's not that complex. And let's, of course, not forget that we also have ARM CPUs built into all of our peripherals. So to put into perspective, this is what we have right now in our modern hardware. It's definitely not something that looks straightforward. And this is not to say that we are screwed totally, but as you might have seen, this is really has been becoming more and more complex. And when you turn on your computer, it actually goes through that entire process from going from real mode to protected mode and running a virtual machine. So these modes are all supported in every CPU we have today. But for cloud security, really all we care about is just this little segment. So we just have the hypervisor and we have the virtual machines. And let's just look at that. And what we want to do there is to secure those virtual machines using the hypervisor. So instead of using your regular antivirus, which runs in ring 3, we want to move that out to a protected separate box so that it's actually protected by the hypervisor, so that we can actually monitor the VM's memory and the hardware and provide some sort of security within the cloud.
Yeah, now with all the hardware security in place, we now want to look at the theoretical concept of virtual machine introspection. What is it and what do we want to achieve with it? What is the problem? So basically, we want to view and also interact a virtual machine from within a host operating system. And that means also not only the memory that we have, but also the virtual hardware, may it be the disk, the network connection, the different CPUs. And for virtual machine introspection, we have 3 different properties that we need our system to fulfill to actually be able to do VMI. And these are isolation, interpretation, and interposition. So first, the isolation part. Yeah? We want to we want to place a security component within the system, and that security component must not be tampered with by any malware. So we need some kind of separation between the security component and the operating system, and thus want to move it out of the guest operating system. And therefore, we use virtualization, and therefore, the hypervisor exposes a very small attack surface for the malware. And for the malware, it's then increasingly harder to tamper with the security system. Increasingly harder, as in I said, yeah, well, VM escapes attacks are possible, but for our scenario where we want to monitor a system and like see the beginning of an attack, this is definitely helpful in the first phase. So we run a system isolated to monitor the virtual machine. The second problem is that we have is when we look into a virtual machine from the outside, and for example, we look at the memory, we see what we have here on the right. Yeah, we see a lot of hex numbers where we don't know what it is, and this is usually called the semantic gap. And the interpretation problem that we have with VMI is that from this binary data, we want to reconstruct the high-level state of the virtual machine that we are introspecting from that data. For example, we have here a Linux system, and we know that we have a struct module here in the beginning, and from the data that is like linked within this data structure, we can then see like what modules are in the system, what memory, what does the memory actually mean, and we can reconstruct the high-level state of the virtual machine, being all the processes running, all the kernel modules running, and what is the system actually doing. And the third thing is now as we know what the system is doing, we also want to interact with the system. So the third thing is the interposition problem. And this means we want to step into the execution of the virtual machine that we are introspecting, and for example, at a certain event, do something from the hypervisor. So we can, for example, prevent an intrusion or analyze the system further. And this mechanism also needs to be very fast, because that is the problem. If you do something in the virtual guest system, then the guest system itself is stopped, and therefore you have a performance impact using this interposition. And also, we need it to be stealthy, because if the malware detects that we are tampering with the malware, so to say, then it could change its behavior. And the last problem with that is that we know from the interpretation thing what like the operating system should do, but we also want to be sure that this is really the state of the operating system, and thus all of the events or all of the information we use must be directly based on the hardware. So we want to, for example, intercept when a page is not readable or writable, and use those hardware events to interact with the system then. So these three aspects, the isolation is mainly provided by the hypervisor, so KVM, Zen, whatever. And the interpretation problem is done by VMI and volatility, so the libraries are able to read the guest system state and make some useful information from it. And the interposition property is mainly provided by the underlying hardware, so the CPU, and also by LibVMI, which provides a usable API for a programmer to use those hardware events and to interact with the system. So after having like the foundation, Tamás will tell us about what LibVMI actually does.
So LibVMI is really a library that targets many use cases. One of them is really system-level debugging. For example, you want to debug an operating system. LibVMI gives you all the tools necessary to be able to just monitor a virtual machine and be able to tell what the operating system is doing from a deep hardware layer. You can use it for analysis, but also for runtime security. So that is, of course, what applies to the cloud. We want to apply it, the runtime security OS integrity checks at runtime for systems that are running on a virtualized system. What I'm using it for my PhD is malware analysis, but you can also use it for forensics, and there are many other use cases that people are looking into as well. So what it is really is LibVMI says low battery. Yeah. So what LibVMI really is this glue in the middle. Okay. That sort of ties everything together. So it lives in the on a user space level, and it's a C library. And what it does, it really provides the interface to interact with the hypervisor layer without having to know the specific hypervisor you are using. So the idea is that you write your application once using LibVMI, and you can just swap out the underlying hardware or hypervisor, and your application just continues to run. So it's an abstraction library. Right now, it supports Zen, KVM, and QEMU, and also supports Intel, AMD, and ARM architecture. So you can actually use this on both servers and your mobile devices. The virtual machines that right now it can make sense of and interpret are Windows and Linux, but there are more planned to come. For example, for the ARM architecture, we are planning to add Android support, so you can actually use this to interpret your Android operating system. The core features are that you can access the memory of that virtual machine from the external perspective. You can both read and write into that memory. And it does the virtual to physical translation for you. So when you're actually looking at the memory, as Tom said, the interposition, you're actually looking at guessed physical memory. But of course, what the process sees is the virtual memory that we have saw that runs in ring 3. So there needs to be a translation happening, which is done through paging. And actually, LibVMI supports all paging mechanisms, so you can just specify which page table you want to use, and the translation is done automatically. It can find and interpret the guest operating structures, so for example, you can find the running processes, kernel modules, things like that that make your life a lot more easier when you're actually starting to develop applications using this. And then, of course, it allows you to place monitoring hooks within that system using various mechanisms provided by the hardware. So for example, exceptions and page faults are the two main mechanisms that we are using to interpose on the execution of that system. There are essentially 4 types of those. The main one is the Intel extended page tables based exception that we can interpose. That is essentially, there is the second page table when the hypervisor goes from the guest physical memory to actual machine physical memory. There is a page table there as well to do the translation, where you can place whatever permissions you want, and then you can monitor the execution of a process within the virtual machine that is actually reading or writing to that memory. You can also catch register events. So for example, the CR3 register is what holds the executing processes page table. So if something gets written to that register, that means that the operating system is scheduling a new application. So it's very handy to get notified when something new gets scheduled within that virtual machine, because it's something meaningful for a higher level semantic layer as well. You can also inject breakpoints, so the int3 instruction can be injected into virtual machines, and that's just a regular breakpoint that even your standard debuggers are using, but can be configured to trap into the hypervisor. And then, of course, you can use single stepping based on the hypervisor as well, which is a stealthy version of the trap flag. To actually look at some demos, because this is all pretty deep, what I have here is a Zen 4.4 system running Windows 7. Don't worry if you can't read the left, I'm going to tell you what's going on there. So this is a 32-bit Windows 7 system running Windows 7 Service Pack 1. And I'm listing all the processes that are running within that virtual machine from an external perspective. So I have Task Manager running in there, and on the left you actually see more processes from the hypervisor level than what Windows tells you. So this already shows you something that is very handy. You can also list all the kernel modules. For example, this is showing all the kernel modules for NTOS kernel. So these are the drivers that are loaded into Windows. So these are all the static things that you can just reconstruct from looking at the memory. But what we also want to do is actually look at the execution of that system. So what I'm doing right now is I'm injecting breakpoints into the system call interface of Windows. And what you see on the left is the actual live execution of the Windows operating system as seen from the hypervisor level. And I'm not really doing anything, and this is all that's happening. Beside the system calls, what I'm also trapping here are heap allocations, so kernel heap allocations. So whenever Windows allocates an object within its memory space to represent whatever process kernel module it wants. It allocates it on the heap, and I can interpose on that. So these are, again, the functions, the system call functions that are being called, and the xallocate pull width tag is the heap allocation function within Windows. And why this is very handy is because you can really target specific behaviors. So for example, the heap allocation is very handy to detect, for example, if you want to see what files are being opened on that operating system. So I can really just grab for the heap allocations, and you see a bunch of things don't really make sense. I mean, there are really a million tags that Windows uses for heap allocations. So you can see things like IO allocations and GDI, XLate, who knows what those are. I really just Google search for the tag and print those out to try to make sense of what Windows is doing. But again, what I was really looking for is the file accesses. So based on this technique, I can actually check what files are being opened by Windows even before those files are open. So this is just Windows allocating a structure to hold the string for the file path in memory. And as you can see, there's a bunch of files being opened just for right-clicking on some standard system menu. And these are all the files that Windows opens in the background that you probably are not even aware of. So it loads all the libraries and folders. And yeah, this is a lot of stuff for just something very simple. This is, of course, quite handy when you are doing malware analysis. This is what I was really building this for, because I was interested in what files malware creates on the file system, or what executables are being dropped by malware on that system, so you can actually really see it from an external perspective before malware can hide it. So as I said, this happens even before the operating system opened those files, so malware had no chance to hide any of these files being opened. So I just created a text file on the desktop, and you can see that it shows up as test.txt.txt. So this is how you interpose on the system to reconstruct high-level semantics about what's happening within. Of course, you don't just want to statically observe what's happening within that VM. You can use all of these hardware events to also perform interposition actively. So this is Windows 7 64-bit. And again, I can just list all the processes that are running. And I have Task Manager running, and what I'm going to do is I'm actually going to hijack the execution of that process to inject a function call to create another process. So I'm just going to inject calculator into that virtual machine. And what's cool about that is that I had nothing special installed within that virtual machine. This was just the standard Task Manager running, and you can really use any application that is running on that system to execute anything else. So there is really no software requirement, so you don't have to install like, your VMware tools or VirtualBox tools to really interact with that system. And really, you can do whatever you want. So I can just fire up command terminal and print hello world, or download an application and automatically install it all through the hypervisor. So again, I did this so that malware analysis is becoming more stealthy. My goal was that malware won't be able to check if you have like something specific to your malware analysis environment present in that system, like a startup script that just gets malware samples. You can really just inject whatever you want, open a website within that virtual machine. So this is all quite handy, and you don't need anything special installed. This is all supported by the Xen hypervisor natively.
Yeah, with that, we want to conclude our talk. Yeah. With that, we want to conclude our talk and talk a little bit about like what's next, what we see as the next open points. So for LibVMI, currently there's support for Linux and Windows to do what Tamás showed. And also, the support will be extended for other operating systems like Android BSD, so that also these systems can be monitored in the cloud. Also, hypervisor support. Currently, Xen is like the main target of LibVMI. KVM is also supported now with an external patch from LibVMI, so there should be better support. Also, VirtualBox, Hyper-V, the hypervisor, you name it, will be supported by LibVMI in the long term. And also, the system was developed for the Intel CPUs, basically. But now, as virtualization is also available for ARM devices, mobile phones, the targets of LibVMI have been enhanced to also support, or are in the run to support, other CPUs like ARM, for example. So this is with that. And as the last thing, we want to talk a little bit like what do we expect next in the cloud. So we think that there are very open topics. For the one thing, we expect that the applications that are run in the cloud usually are now you replace a host that you have like in your basement and put it to an instance in the cloud, which is like self-contained. But what should happen is like that the application should be divided in like the front-end service databases, and this network of applications that interplay with each other should be monitored using, for example, LibVMI as in a network-based intrusion detection system, so that the systems itself can be monitored in a more advanced way. And currently, the software is available. It's available in the cloud, so such things could be done by Amazon, for example. But the cloud providers do not yet provide access to those features for their customers. But we think that's an important problem that should be solved. And on the other hand, as I said, the hardware or the hardware features that we are leveraging are all also available on the smartphones and tablets. So using these technologies, these technologies can also be used to secure end-user systems and to aid like the antivirus software to monitor end-user systems in a more advanced way. Yeah, from this, we thank you for our attention and are open for any questions.
So is it already the case that there are applications that use this kind of monitoring, or is it just that it's feasible by now? I got the impression with your kind of interaction with the guest operation system that this might kind of slow down. I mean, it looks like you're running your application through a debug mode or so.
It is actually very close to a debugger. So that application has actually been the drugproof system, so that's the malware analysis. So that one is already available, and you can download it and install it, and that is really targeting malware analysis. I'm aware of commercial companies coming out with products based on similar technology. It's probably targeting enterprise customers right now, so it's not something you could buy for your laptop, for example. But definitely there are things that are using virtualization and similar techniques to enhance protection systems.
And like for the performance drawback, so my actual research target is to ensure the integrity of an operating system using this technology. And using my system, my performance decrease is like less than 0.5%, so you can really use it on a live system.
Do you think that the performance decrease could be used by malware to actually detect that it's being handled?
Well, that is a problem that is not solvable, but because all the servers are time synchronized using NTP, so there's no way to hide the timing information from malware. But we think that more and more systems will be virtualized. Yeah, you have the virtualization extensions in your smartphones. There's the trust zone, secure zone, a little bit technical background. But in the end, many systems are virtualized as is. So the malware will be running in a virtual machine anyway. And it cannot know, is this virtual machine monitored or is it not monitored? Exactly.
It can't detect like the delay that comes from the probing.
That's exactly where we said the interposition thing has to be both stealthy, that the malware can detect it as is, and also very fast and efficient, that these timing constraints are not that big of a deal. And as Druckwolf shows, this is doable.
Yep. Yeah, exactly. So the breakpoints that are actually injected here for the tracing are actually invisible to anything within that virtual machine. So even if a kernel mode rootkit will start scanning the kernel pages to see if there are breakpoints injected, I can check and I can actually trap when the kernel rootkit tries to read those pages. So when something tries to read it, I can just remove the breakpoints, let it read through, and then place it back right after that. So it's actually execute-only code injection into the virtual machine. Nothing within that machine can detect that the code has been modified, which was actually a requirement because Windows does that natively. The patch guard actually detects. So if I would just inject those breakpoints, Windows would crash. So I actually had to detect when Windows itself was checking if it was modified in order to let it progress. So this is already a stealthy mode of observation.
What are the conceptual difficulties if you want to monitor, say, Docker containers with something like this?
So Docker is actually an operating system based containerization method. So there is no hypervisor involved, there is just your operating system. So it's really something that you could just implement a kernel driver for and you would have access to the memory of that container. From the hardware perspective, there is no difference between that and just introspecting a process natively.
But the isolation component of VMI is missing in the Docker use case.
Did you say this requires installing nothing on the host, or I mean the guest?
Yes. Yes, that's correct.
So how do you make it execute something? How do you know that it's in a state where you can?
That is a complex setup, as you might imagine. So the idea is that you can detect, for example, when a process gets scheduled. So that's the write to CR3 register. You can trap that to the hypervisor. Problem is at that point, the process is still running in kernel mode. You need to detect when it actually switches to ring 3. So what you can do there, you have various mechanisms. You can either single step till it actually reaches ring 3 code, or you can use operating system semantics. So for example, what I do with Druckwolf, I actually read the trap frame from the stack, and I can tell what return address will be called when it goes back to user mode, and I just inject a breakpoint there so I get notified when, okay, this is the first execution of the user mode. I can just inject whatever function call I want to at that point by modifying the stack again. There are certainly other ways to do that, so signal injection would be probably the most straightforward alternative to do that.
Signal injection?
Yes, signal injection.
Wouldn't that show on the guest?
Say that again?
If someone's tracing signals on the guest.
Yeah, so it wouldn't be signal injection in the standard way. So you would actually just place the structure into the signal queue by writing it into memory, and that would only get called when the process actually hits user mode. So it's actually only in that process's space. And you can also detect that if something is trying to read from that signal queue, if it's the process that you want to read from that queue. So it would work. Actually, this is the same method that Cuckoo is using right now in the advanced mode to inject the execution of new malware. So, any other questions? All right, well, find us later if you guys have any questions or get in touch. It's all open source, so community involvement is always welcome. So, thank you.
Yeah, thank you.